But before we do that, let's do a really quick recap. So the recap, the curl of f is defined to be the gradient cross the vector field. Notice that what you received after you did the gradient cross the vector field, because it is a cross product, you end up with a vector. It yields a vector. If you were to take the divergence, however, of f, that was the gradient dot the vector field. That will give you some kind of a function. In our example up there, we ended up with things in terms of z's. And the gradient of f is defined to be the partials, which is also a vector. So if you take a vector and you dot it with another vector, you ended up with some kind of a function. Could be a constant, but remember, constant's a function. And then if you take a gradient and you cross it with a vector field, you end up with a vector. That's our recap. Now let's take a look at the actual geometric interpretation of this. All right, our last example says the vector field f is shown in the xy plane and looks the same in all other horizontal planes. In other words, f is independent of z, and its z component is 0. So basically, we're looking at a two-dimensional vector field in this case. And if you looked at any other plane, the vector field would look exactly the same as long as that plane is parallel to the xy plane. So the first part, part A, it says, is the divergence of f positive, negative, or 0, and explain. And then we'll come back to part B in a second. So here's the general geometric idea of divergence. The divergence is asking us if we were to draw some kind of a space. Now the space could be a rectangular or an elliptical or something non-traditional, just some kind of like a blip on there or something. For ease of our example, we're simply going to do something which is circular. So maybe something like that. It's asking us if the divergence is positive, negative, or 0. So divergence basically means this. There's a certain amount of flow that's going into this vector field. Hopefully what you can see is that this vector right here, which is going in, is the same as this vector going in, which would be technically the same as this vector, which would be the same as this vector. They all have exactly the same length, so it looks like the direction and magnitude are identical. But then as you can see, the vectors start to get smaller as we go up this direction. So what it looks like to me is that the amount that's going into this region, into our circular region in this case, is more than is actually going out. So we're actually receiving more into the region than we are going out of the region. The divergence says that if you've got more coming in than you do going out, then your divergence is negative. Vice versa, if you've got more going out than is coming in, then you've got a positive divergence, or something diverging, leaving, moving away from. So if you've got more moving away from the region that you're talking about, you'll have a positive divergence. If you've got more coming into the region than is leaving, so less is leaving than is coming in, you'll have a negative divergence. So let's go ahead and write that down real quick. So if more is going into the region the divergence is negative, because basically what that means is you have less going out. So negative divergence. Likewise, if more is going out of the region, the divergence is positive. So looking at our example right here, it's pretty clear to see from this that no matter where we are in that circle, more is going into the region than is coming out. So in part A, our answer would be the divergence of f is negative. Again, More is coming in than is going out. So you have a negative divergence. Not enough is leaving. Not enough is diverging from our region. So it's negative divergence. Part B now is a different story. That's asking us to determine whether the curl of f equals 0. And if not, in which direction does the curl point? Okay, that's actually a pretty important concept. Here is the general idea for curl, at least geometrically, the general idea. So the curl is basically the tendency for your region or your vector field to rotate the region. So in other words, if I was to put, like, I don't know, the best way to describe this, if I was to put like little paddles all along the edge of this thing right here. This is not what you would really do, but it just gives you a good general sense. If you put little paddles there, and this thing was like sitting in a river or something, and the flow of the river was the vector field, how much rotation would the vector field do to my region? So would it push it in one direction or another? Would it push it clockwise? Would it push it counterclockwise? Or would it not push it in any direction at all? So in this case, it looks like because the vectors that are going vertically against this thing are exactly the same magnitude, it's probably not going to rotate this thing at all. There would not be any kind of a rotation. So in our example right here, for letter B, it looks like the curl of f does indeed equal 0. This does not seem like it's going to have any kind of a rotation. Now I'm going to go ahead and show you on the bottom piece here that won't always be the case, obviously, and show you what one would look like that does have a rotation. So let's go ahead and, again, just for sake or ease of this thing, let's go ahead and just put another circular region down here at the bottom. Probably be the easiest thing to look at would just be something circular. Again, it doesn't have to be. It could be a square, rectangle, triangle, or just, again, some kind of whatever kind of a blob kind of a thing or whatever. But so for our circular region right here, it looks to me quite a bit like these vectors up here on the top part are pushing at a pretty good rate, while the vectors on the bottom are going in the opposite direction, as you can see by the indication of where the arrows are. It looks like this thing would probably be rotating that way because of the strength of the vectors and the way that the vectors are pointing. It looks like you would have some kind of a clockwise rotation. This is the way I think about the rotation here. So we're actually going to answer part B first. We're going to do part B of this. Appears to be in a clockwise rotation. So the curl is definitely not 0. Curl of f is not 0. So if you've ever and if you haven't done this, then you don't probably have the reference that I do, but if you've ever done something where you're screwing something into like a board or a piece of metal or whatever, if you turn it clockwise, the screw is actually going to be going down into the piece that you're screwing it into. That's the way a screw is threaded. And that's a clockwise rotation. I don't know if you ever heard righty-tighty, lefty-loosey. Righty-tighty means you're turning the screw to the right, or in a clockwise rotation, it's going to be pushing the screw into the board. Well, if you think of the top of this circle as being the head of the screw and you're pushing it into the board, you're actually going down past the XY plane, which would be the negative direction. So this is actually in a negative curl rotation because it is a clockwise rotation. Again, think of the screw as being pushed down into the board. It's going into the negative Z direction if you were to make this into 3 dimensions. So this would be a negative curl. That's a clockwise rotation. If it was going the other way, counterclockwise, you'd be pulling the screw out. That's the lefty-loosey part. So the screw head would actually be going in the positive Z direction. So let's go ahead and put that, let's put that up here. If we go clockwise, so a clockwise rotation is a negative z direction. Whereas a counterclockwise rotation is a positive z direction. All right, and then let's go ahead and answer real quick part A of this one. Part A is asking us the same thing as it was before. What is the divergence? And what you should be able to see is that what appears to be coming in at any point seems to be exactly the same that's going out. Up here in the top, these vectors are all exactly the same magnitude. Right here in the middle, they're all the same magnitude. Even going this direction, coming in from here, they're all the same magnitude in that one horizontal line right there. So it appears to be whatever's coming in is exactly the same as what's going out. So in this case, we would say that the divergence of this thing more than likely is 0. Now there's no way to show that exactly, but that's a pretty good estimation from the drawing. Okay, hopefully curl and divergence was not too difficult. That should be a relatively easy assignment.